What if I told you the greatest journey in the history of exploration is still happening right now tonight, in total darkness, and almost nobody is paying attention anymore? And what if the machine making that journey was never supposed to be the star of the show, yet it ended up seeing things its famous twin never could? Before we go any further, do something for me real quick. Hit like, subscribe, and send this video to one person who still gets chills thinking about deep space. It takes 2 seconds. It genuinely keeps this channel alive, and trust me, the story you're about to hear deserves to travel as far as the spacecraft it's about. Now settle in, because this is the story of Voyager 2, the quiet one, the so-called backup, the machine that visited worlds no human eyes had ever truly seen, and then kept going until it left the sun's protection behind forever. To understand why Voyager 2 matters so much, you have to go back to a moment most people have never heard of. In 1965, a young graduate student at NASA's Jet Propulsion Laboratory named Gary Flandre was given a fairly boring assignment: study possible trajectories to the outer planets. While playing with the math, he noticed something extraordinary. Roughly once every 176 years, Jupiter, Saturn, Uranus, and Neptune line up in a way that lets a single spacecraft use the gravity of each giant planet to slingshot itself toward the next one. Miss that window, and you wait almost 2 centuries for it to open again. The next window was coming in the late 1970s. NASA had a choice: build something bold and go, or let a once-in-2-lifetimes opportunity drift past. They chose to go. 2 identical spacecraft were built, Voyager 1 and Voyager 2. Each one weighed less than a small car. Each carried instruments designed in the early 1970s, computers with a fraction of the memory of a modern car key, and a nuclear power source to keep them alive in the dark. And the margins were razor thin. The budget was tight, the schedule was brutal, and some at NASA argued the whole thing was too ambitious, that reaching even Jupiter and Saturn reliably would be achievement enough. The engineers quietly disagreed. They built the spacecraft tougher than the official mission required, with redundant systems layered on top of redundant systems, because a few of them were dreaming, even then, of going all the way. Nobody put Neptune in the official mission title, but more than a few people at JPL built this ship as if Neptune was the plan all along. And here is a detail that surprises almost everyone. Voyager 2 actually launched first. It lifted off on August 20th, 1977. Voyager 1 followed 2 weeks later on a faster path that would eventually let it overtake its sibling. From the very beginning, Voyager 2 was second in line, second in the headlines, second in the public imagination. Voyager 1 would get the glory of arriving first at Jupiter and Saturn. Voyager 2 would get something else entirely. It would get the impossible itinerary. The original plan called for both spacecraft to visit Jupiter and Saturn. That alone would have been a triumph. But the mission designers had quietly built Voyager 2 for a bigger gamble. If it survived its first 2 encounters in good health, its path could be bent toward Uranus and the Neptune, 2 planets so distant that no spacecraft had ever attempted to reach them. Uranus is nearly twice as far from the Sun as Saturn. Neptune is so far away that sunlight, which takes 8 minutes to reach Earth, takes more than 4 hours to get there. No probe had ever operated that far out. Nobody knew if a machine built with 1970s technology could stay alive long enough, stay warm enough, and stay accurate enough to pull it off. Voyager 2 would be flying into territory where failure meant silence, and silence meant forever. Jupiter came first. Voyager 1 swept past in March of 1979, and Voyager 2 followed that July. Together, they transformed Jupiter from a blurry, stripe-covered ball in telescope photos into a living, violent world. Voyager 2, arriving months after its twin, had a strange advantage. Voyager 1 had acted as the scout, finding the surprises, and Voyager 2's team could reprogram its cameras to go hunting for the best targets with better lighting and closer looks. They watched volcanoes erupting on the moon Io, the first active volcanoes ever found beyond Earth. They saw hints of a hidden ocean beneath the cracked ice shell of Europa, an idea so radical at the time that many scientists dismissed it. Today, that hidden ocean is one of the most important targets in the search for life. Then came Saturn, with its impossible rings resolved into thousands of braided ringlets. And it was at Saturn, in November of 1980, that the paths of the twins split forever. Voyager 1 was ordered to make a close pass of Titan, Saturn's enormous orange moon, the only moon in the solar system wrapped in a thick atmosphere. It was a worthy target. But the Titan flyby came with a price. The gravity bend needed to skim Titan flung Voyager 1 upward, out of the flat plane where all the planets orbit. From that moment on, Voyager 1 could never visit another planet. Its planetary career was over. It would climb north out of the solar system, famous and finished. Every planet still waiting out in the dark, every secret still hiding at Uranus and Neptune, now belonged to one spacecraft and one spacecraft alone. If Voyager 2 died, the Grand Tour died with it. If a gyroscope failed, if a radio broke, if a single frozen valve stuck at the wrong moment, humanity would not get another chance at these worlds for generations. Maybe ever. Voyager 2 passed Saturn in August of 1981 and took the bend. It was now aimed at Uranus, a planet almost 2 billion miles farther out. The flight would take 4.5 years. 4.5 years of silence, of cruising through empty blackness, of engineers on Earth nursing an aging machine that was never designed to last this long. And here is where the story starts to feel less like engineering and more like something human. There were scares along the way. The main radio receiver developed a fault, and for one terrifying stretch, the backup receiver had a failed capacitor that made it deaf to commands sent at the wrong frequency. Engineers had to learn to talk to their own spacecraft in a slightly different voice forever. The scan platform, the moving arm that points the cameras, had jammed briefly at Saturn, and nobody knew if it would jam again at Uranus, right in the middle of the most important pictures of the mission. But the team at JPL did not just keep Voyager 2 alive. They reinvented it in flight, they uploaded new software, taught it new tricks, squeezed better performance out of cameras and radios that were already old when disco was new. They knew that at Uranus, the sunlight would be 400 times weaker than at Earth. Pictures that were easy at Jupiter would become long, delicate exposures at the edge of the dark. The spacecraft would have to hold itself impossibly steady while its camera stared and stared. Any vibration, any drift, and the images would smear into uselessness. So they rehearsed, for years, while the ship flew on through nothing. Quick pause, and I promise it matters. Somewhere out there, right now, a machine built by people with slide rules is still whispering data back to Earth. If you think stories like this deserve more attention than the usual noise on this platform, subscribing is how you prove it. And if you have already subscribed, dropping a comment telling me where in the world you are watching from genuinely helps this video find more people. All right, back to the dark. And then, history intervened in the cruelest way. Just 4 days after the Uranus flyby, as the data was still pouring in, the Space Shuttle Challenger broke apart 73 seconds after launch, live on television, killing all 7 astronauts aboard. The scientists at JPL were suddenly juggling the greatest triumph in the history of planetary exploration, and one of the darkest days in the history of the space program. In the same week, in the same building. The president's planned celebration of Voyager quietly disappeared from the news. Uranus, the greatest discovery of the decade, was nearly buried by grief. It is one of the reasons so few people remember this flyby at all. But the science was immortal. On January 24th, 1986, Voyager 2 had reached Uranus. And this is the moment where the title of this video starts to make sense, because no spacecraft before it, including Voyager 1, had ever done this, and no spacecraft since has done it again. To this day, Voyager 2 remains the only machine humanity has ever sent to Uranus. Everything you have ever seen in a textbook about this planet, every close-up image, every measurement, every fact your teachers repeated, comes from a few frantic hours of flyby by a spacecraft that was already 9 years old and 2 billion miles from home. And Uranus was weird. Even from a distance, astronomers knew it was the oddball of the solar system. While every other planet spins like a top, more or less upright, Uranus is lying on its side. Its axis is tilted about 98 degrees, which means it essentially rolls around the sun like a barrel, taking turns pointing each pole almost directly at the sun. Nobody knew why. Something enormous, early in the planet's history, had apparently knocked it over. Voyager 2 was about to meet the strangest giant in the family, face to face, with no second chances and no backup. The flyby was a masterpiece of precision. Voyager 2 threaded through the Uranian system at tens of thousands of miles per hour, passing within about 50,000 miles of the cloud tops, close enough to study the planet, its rings, and its moons in a single sweeping pass. And almost immediately it started overturning expectations. Astronomers expected Uranus to be boring, a bland, featureless cue ball, and on the surface, visually, it kind of was. The atmosphere showed almost no clouds, almost no storms, a pale blue-green sphere wrapped in haze. But the instruments that measured things human eyes cannot see found a planet that was anything but boring. Start with the magnetic field. Every giant planet visited before had a magnetic field roughly aligned with its spin, like a bar magnet standing up through the middle. Uranus threw the rulebook away. Voyager 2 found that the magnetic field of Uranus is tilted nearly 60 degrees away from its rotation axis, and it is not even centered. It is offset from the middle of the planet by about a third of the planet's radius. Imagine a bar magnet inside a spinning ball, but the magnet is shoved off to one side and tipped over at a wild angle. As Uranus rotates, that lopsided field corkscrews through space, dragging the planet's whole magnetic environment into a bizarre, twisted shape. Scientists had never seen anything like it. The leading theory says the field is not generated deep in a metallic core like Earth's, but in a strange, slushy layer of compressed water and ammonia ice partway down, a kind of ocean unlike anything on our planet. One flyby, and the physics of how planets make magnetic fields had to be rewritten. Then there were the rings. Uranus's rings had been discovered from Earth only 9 years earlier in 1977 by pure luck, when the planet passed in front of a distant star, and the starlight blinked on and off. 9 narrow dark rings were known. Voyager 2 found 2 more and photographed the whole system up close for the first time, revealing rings made of some of the darkest material in the solar system, charcoal black bands of debris, thin and sharp, shepherded by tiny moons nobody had ever seen. And speaking of moons, Uranus had 5 known moons when Voyager 2 left Earth. By the time it left Uranus, that number had jumped to 15. 10 brand new moons discovered in a matter of days. But the real showstopper was a moon we already knew about, Miranda. Miranda is small, barely 300 miles across, a frozen speck compared to Earth's moon. Astronomers expected a dead, cratered ice ball. What Voyager 2 photographed instead made jaws drop across the entire planetary science community. Miranda looks like it was shattered into pieces and then sloppily glued back together. Its surface is a jumbled patchwork of completely different terrains stitched side by side. Ancient cratered plains jammed against bizarre grooved regions that look like giant racetracks. There are enormous chevron-shaped scars, vast canyons, and cliff faces, so tall they defy belief. One of them, Verona Rupes, is estimated to be up to 12 miles high. That is roughly 10 times the depth of the Grand Canyon. On a moon with gravity so weak, you could throw a ball into the sky and watch it hang there. If you fell off that cliff, you would fall for something like 10 minutes before hitting the bottom, and because the airless gravity is so gentle, a survival suit might actually save you. Nothing in the solar system looks like Miranda. To this day, scientists argue about whether it was smashed apart by a colossal impact and reassembled from the rubble, or whether it was churned from the inside by geological processes we still do not fully understand. Voyager 2 gave us one look, just one. And it has been enough to fuel arguments for 4 decades. There was one more shock hiding in the data, and it was a quiet one. Every giant planet visited before radiated more heat than it received from the sun. Jupiter, Saturn, they all glowed with leftover warmth from their formation. Uranus, Voyager 2 discovered, barely radiates any internal heat at all. It is, energy-wise, almost dead inside, the coldest planetary atmosphere in the solar system, colder even than Neptune, which sits much farther from the sun. Why? Nobody fully knows. Maybe that ancient collision that knocked the planet over also dumped its internal heat into space. Maybe something about its strange interior traps the warmth below. Whatever the answer is, it is sitting on a planet we have visited exactly once for a few hours, 40 years ago. I want to take one breath here, because what happens next only happens once. If this story has earned a place on your screen so far, tap like right now, not for me, but for the engineers who flew a machine 2 billion miles and hit a target the size of a city. And if you are new here, this is the moment to subscribe, because we are only halfway to the edge of the solar system. And then it was over. In the time it takes to watch a long movie, Voyager 2 had come screaming through the Uranian system, hoovered up everything it could, and was already gone, flung by Uranus's gravity toward an even darker destination, the last giant, Neptune. A planet so distant that when Voyager 2 launched, many of the engineers who built it doubted privately that the spacecraft would still be alive to see it. The journey would take 3.5 more years. The sunlight out there falls to 1/900th of what we enjoy on Earth, and the spacecraft was now 12 years old, running on a decaying nuclear battery, its parts aging, its thruster fuel precious, billions of miles from any possible rescue. The team, back home, had a nickname for what they were attempting. They called it the Impossible Encore. Now, if you are still with me at this point, you're exactly the kind of person this channel exists for. So here's a different kind of ask. Do not just subscribe. Pick one person in your life who thinks space is boring and send them this video. That is the real test. Because by the end of this story, I'm willing to bet they will not think that anymore. Neptune is waiting. Neptune holds a special place in the history of science because it was discovered with a pencil before it was ever seen through a telescope. In the 1840s, astronomers noticed that Uranus was not moving exactly the way Newton's laws predicted. Something unseen was tugging on it. 2 mathematicians, working independently in England and France, calculated where the hidden culprit had to be. In 1846, astronomers in Berlin pointed their telescope at the predicted spot, and there it was. Neptune, found by mathematics, a triumph of human reasoning over pure darkness. But for the next 143 years, that is all Neptune remained, a dim blue point of light. Even in the best telescopes on Earth, it showed almost nothing. No features, no moons worth counting beyond 2, no answers. Then, on August 25th, 1989, Voyager 2 arrived. The tension in the final weeks was something people at JPL still talk about. A failure at Neptune would not just lose a few pictures. It would erase the only close look at an entire planet humanity might get for a century or more. There would be no second spacecraft. There was no follow-up mission approved, none even proposed. Whatever Voyager 2 brought home from Neptune would be, for all practical purposes, the sum total of human knowledge about that world for the foreseeable future. And as the images started sharpening in the approach, the scientists realized something unsettling. Neptune had clouds, bright ones, which meant Neptune had weather, and weather meant the flyby could be ruined by something as simple as bad aiming at a fast-moving target wrapped in moving haze. And Neptune, the planet everyone assumed would be a colder, duller version of Uranus, turned out to be spectacular. The encounter plan was audacious to the point of madness. Neptune is 30 times farther from the Sun than Earth. The radio signal from Voyager 2, traveling at the speed of light, took over 4 hours to reach home, and it arrived with a strength of about a billionth of a watt. Engineers had to link radio dishes together across continents just to hear the whisper. The light was so faint that camera exposures stretched toward 10 minutes long, and at those speeds, the spacecraft's own motion would blur every image. So the engineers did something nobody had ever done. They reprogrammed Voyager 2 to fire its tiny thrusters in delicate pulses during each exposure, rotating the entire spacecraft to compensate for the motion, essentially teaching a 12-year-old machine to track its targets like a photographer panning with a speeding race car, billions of miles away, with 1970s hardware. It worked. The first images that came back showed a deep blue world with bright white clouds streaking across its face and dominating the southern hemisphere, a dark storm so vast that the entire Earth could have sunk into it. They called it the Great Dark Spot. It was a hurricane the size of a planet, and it was spinning on a world that receives almost no energy from the sun. That should have been impossible. Storms need energy. Neptune gets almost none. Yet Voyager 2 measured winds in Neptune's atmosphere blasting along at up to 1 in 300 miles per hour. The fastest winds in the entire solar system, on the planet farthest from the sun. To this day, the winds of Neptune remain one of the great unsolved puzzles of planetary science. Nobody can fully explain where the energy comes from, and here's the kicker. When telescopes looked at Neptune just 5 years later, the Great Dark Spot was gone. Vanished. A storm bigger than Earth, here and then not, on a planet we only ever got to see up close once. Voyager 2 also revealed that Neptune radiates about 2.5 times more energy than it receives from the sun, making it the opposite of Uranus in yet another way, hot-hearted, alive, churning. 2 ice giants, born from the same cloud, roughly the same size, and yet one is comatose and the other is furious. Nobody predicted that. Nobody could have. That is the thing about real exploration. The universe keeps refusing to follow the tidy patterns we invent for it. Then came the encore within the encore. The mission planners had saved one final gamble for the very end. Instead of flying past Neptune at a safe, sensible distance, Voyager 2 dove to within about 3,000 miles of the planet's north polar cloud tops, the closest approach it made to any object on its entire 12-year journey. Why? Because they wanted Neptune's gravity to grab the spacecraft and hurl it downward, south, out of the plane of the planets, on a path that would carry it directly past Neptune's giant moon Triton just hours later. It was a gravity trick inside a gravity trick, the most precise maneuver of the entire mission performed at the edge of the known solar system, and it delivered the single most haunting world Voyager 2 would ever see. Triton is, quite simply, one of the strangest places in existence. It is slightly smaller than Earth's moon, covered in nitrogen and methane ice with a surface temperature of around minus 391 degrees Fahrenheit. It is so cold that nitrogen, the very air you're breathing right now, falls there as snow. Voyager 2 found a surface that looked like the skin of a cantaloupe, wrinkled and pitted. Almost no impact craters, which meant the surface was young, active, renewing itself. And then the cameras caught something that stunned the scientists watching back home. Dark streaks rising miles into the thin atmosphere. Geysers erupting on a moon at the frozen ragged edge of the solar system. The leading explanation is as elegant as it is strange. Sunlight, weak as it is, passes through Triton's transparent nitrogen ice and heats the darker layers beneath, turning nitrogen to gas, building pressure until the ice above gives way and the geyser blasts skyward, carrying dark dust with it. Cryovolcanism, powered by sunlight barely strong enough to read by. The scientists watching the first streak images arrive reportedly sat in stunned silence. And then someone said the obvious out loud. The moon was supposed to be dead, frozen solid, geologically finished. Instead, it was active, erupting, alive at a temperature where chemistry itself nearly stops. Nobody, had ever imagined such a thing. And there was one more twist. Triton orbits Neptune backwards against the planet's rotation, a telltale sign that Triton is not Neptune's child at all, but a captive, a world from the Kuiper Belt, the ring of icy debris beyond Neptune, grabbed long ago and dragged into its current orbit. Pluto, it turns out, is probably Triton's long-lost sibling. Voyager 2 had not just visited a moon, it had given us our first real look at an entire class of worlds that would not get their name, Kuiper Belt objects, until years later. 6 new moons. A storm bigger than Earth, the fastest winds ever recorded, a backwards moon with ice volcanoes, and a planetary ring system found to be clumped into strange bright arcs that defied easy explanation. All of it gathered in a matter of days, by a spacecraft running on less power than a refrigerator light bulb, 4.5 billion miles from home. And when the last Triton image was taken, Voyager 2 turned its cameras off for the final time. Its planetary mission, the grand tour dreamed up by a graduate student in 1965, was complete. Jupiter, Saturn, Uranus, Neptune. 4 giants in 12 years. A feat never repeated, never even attempted again. Here's where I need you to do one more thing, and this one is personal. Stories like this are vanishing from this platform, buried under an avalanche of noise. If you want to make sure you never miss one, hit the notification bell after you subscribe, and leave a comment with just 2 words, "Still exploring." When I see those comments, I know this work matters to someone out there. Now, the part of the story almost nobody tells. Because for Voyager 2, the end of the planets was only the halfway point. After Neptune, both Voyagers were racing out of the solar system on different paths, Voyager 1 heading north, Voyager 2 heading south. Their new mission had a new name, the Voyager Interstellar mission, and a new goal: find the edge. Somewhere out there, the sun's influence simply stops. The sun blows a constant stream of charged particles in all directions, the solar wind, and that wind inflates a vast bubble around our entire solar system. Called the heliosphere, everything inside the bubble is, in a sense, still home. Outside it lies true interstellar space, the raw galaxy, filled with particles and radiation from ancient exploded stars, from other suns, from the deep history of the Milky Way itself. Nobody knew exactly where the boundary was. Nobody had ever been there. The edge of the bubble, the heliopause, was a theoretical line on a diagram, guessed at, argued over, never measured. Voyager 1 got there first. In August of 2012, at a distance of about 11 billion miles from the sun, its instruments detected a dramatic change. The solar particles vanished and galactic cosmic rays flooded in. Voyager 1 had crossed the heliopause. It was a historic moment, the first human-made object to enter interstellar space. The headlines ran around the world. But quietly, in the scientific community, there was an ache in that triumph, because Voyager 1 had a wound. Its plasma science instrument, the one tool specifically designed to directly measure the charged particles of space, had failed back in 1980, shortly after Saturn. For 32 years, it had flown blind in that one crucial sense. When Voyager 1 crossed the greatest boundary in exploration history, it could feel the change indirectly, through secondary instruments, through clever detective work, through vibrations in the plasma rather than the plasma itself. But it could not taste the interstellar medium directly. It could not measure the temperature, the speed, the density of the actual stuff of deep space. As it crossed the line, it crossed the finish line with its most important sense switched off. Voyager 2's plasma instrument still worked. 6 years later, on November 5th, 2018, Voyager 2 crossed the heliopause, at roughly the same distance from the sun as its twin, but on the opposite side of the bubble, heading south instead of north. And because its plasma instrument had survived the whole journey, Voyager 2 did the one thing Voyager 1 never could. The crossing itself was not a guess. The data left no room for argument. The plasma instrument watched the solar wind, the breath of the sun that had been blowing, past the spacecraft for 41 years, suddenly fall away to almost nothing. And on the far side of the boundary, it found the plasma of interstellar space waiting, colder and denser than expected, pressing inward against the bubble like an ocean against a hull. It directly measured the plasma as the spacecraft passed through the boundary itself. It tasted the solar wind dying away, felt the particles thin out, and then measured the interstellar plasma on the far side, denser, colder, stranger than almost anyone had predicted. For the first time in history, humanity had a continuous, direct readout of what it feels like to leave a star. Not a model, not an inference, a measurement, taken by a machine launched when most of the people watching this video were not yet born, carrying a computer less powerful than the chip in your washing machine. And what it found rewrote the textbooks again. The 2 crossings, north and south, happened at nearly the same distance, which told scientists the heliosphere is far more symmetric than many models assumed. The boundary turned out to be astonishingly thin and sharp in places, a genuine Wall between two cosmic environments, yet leaky too, with solar material seeping outward and galactic rays sneaking inward across a transition zone that does not behave the way tidy diagrams promised. Voyager 2 watched the plasma get hotter in a compressed layer just outside the boundary, like water piling up against the hull of a moving ship, a bow region nobody had ever directly observed before. It measured magnetic fields that refused to change direction at the boundary the way theory said they should, a puzzle that is still unsolved today. Every one of those measurements is now the foundation of an entire field of science, and every one of them exists only because one instrument on one spacecraft refused to die for 41 years. Think about what that means for a moment. Two probes, identical twins, built by the same hands, launched the same summer. One got the fame, the firsts, the headlines. The other got the 4 planets, the sideways world, the ice geysers, the impossible moon, and then, in the end, the one measurement its sibling could never make. Voyager 1 crossed into interstellar space first. Voyager 2 is the one that told us what interstellar space is actually made of, and the mission is not over, not even now. There was even a moment not long ago when we nearly lost it to a simple mistake. In the summer of 2023, a routine command sent from Earth contained a tiny error, and Voyager 2's antenna drifted 2 degrees off target. 2 degrees. Across 20 billion kilometers, that was enough to sever the link completely. The most distant conversation in human history went silent, and nobody knew if anyone would ever hear it again. Engineers scrambled, listening with the most sensitive ears on the planet. And then, weeks later, the giant antennas of the Deep Space Network caught it. A carrier signal so faint it barely rose above the noise of the universe itself. They shouted a corrected command into the dark at maximum power and waited 37 hours for a reply. And the old machine, faithful as ever, turned its ear back toward home and answered. As you watch this, Voyager 2 is more than 21 billion kilometers from the sun, still coasting, still reporting. Its radio signal weaker than a trillionth of a watt by the time it reaches Earth. Takes around 20 hours just to get here at the speed of light. When engineers send a command and receive an answer, a full day and a half has passed. The spacecraft is powered by the slow radioactive decay of plutonium, and every year it loses about 4 watts of power. One by one, NASA has been switching off heaters and instruments to keep the survivors alive, sacrificing the margins of safety to buy more time. The team estimates they can keep at least one instrument running into the 2030s, maybe longer, through tricks that border on miraculous, like rerouting power from a voltage regulator built decades ago to squeeze out a few more years. Every single day of data now is a gift from engineers who were not yet born when the spacecraft launched, keeping alive a machine whose schematics exist on paper older than they are. And someday, probably within the next decade or so, the end will come. There will be no explosion, no dramatic finale. One day the power will simply fall below the minimum, and a whisper that has been traveling toward us for nearly 60 years will stop. Voyager 2 will not notice. It cannot feel. It will simply keep flying, silent, dark, still carrying its golden record. The famous gold-plated disc filled with the sounds and images of Earth, greetings in 55 languages, whale song, thunder, a mother's kiss, Bach and Chuck Berry, a message bolted to the side of the most distant emissary our species has ever made. In about 40,000 years, it will drift within a couple of light years of a star called Ross 248, and roughly 300,000 years it will pass within shouting distance, cosmically speaking, of the brilliant star Sirius. It will outlive the pyramids. It will outlive every language spoken on the record it carries. It may well outlive us. So when people ask why Voyager 2 matters, why a machine older than most of its operators deserves a story told about it nearly half a century after launch, the answer is not just the planets, as astonishing as they were. It is not just the rings and the geysers and the sideways magnetic fields. It is what the whole journey proves about us. A species that figured out it had one chance, once every 176 years, to see the giants of its own solar system and took it. A species that built a machine so well that it outlived its designer's wildest hopes, visited 4 worlds and then just kept going, out past the edge of the sun's reach, into the space between stars, still sending home postcards from the void. Voyager 1 will always be the first to leave home. But Voyager 2 is the one that saw the most, measured the deepest, and went where nothing else has ever gone, before or since. It did what its twin never could. And somewhere out there tonight in the cold and the dark, 20 hours from the nearest human voice, it is still doing it. Still flying, still whispering, still carrying a golden record full of who we were, towards stars that have not heard from anyone ever. That is not just a machine. That is the best of us, launched on a summer day in 1977 and never called back.